Hernán?
Yeah, sure. Yes.
Good morning and good evening for some others. Let's start our today session. The first speaker is Professor Hernán Makse from City College of New York. He'll talk about how network theory and contact tracing can help to stop COVID-19 pandemic. We have 25 minutes, and I asked that the questions should be made in the chat, okay? And after the presentation, the speaker will answer the questions. If you have time, if you don't have time, he will answer in the chat, okay? You can start, Hernán.
All right, thank you so much, Nuno, and thank you so much to Celia and all the organizers for the invitation. It's a great pleasure to be, here with you today. Although a little bit sad that we are not actually all together enjoying the wonderful city of Sao Paulo. But anyway, so today in this talk, I'm going to tell you a story of how we ended up working on trying to understand the spreading of COVID-19. I was actually working with this wonderful set of people in a collaboration with Professor Suarez and Saulo Reis from UFC, the Universidade Federal de Ceará, in Fortaleza. So at that time, it was March 2020, and we were hit by the pandemic in New York, and also it was starting at the same time in Brazil. And at that point, with my group and many other people, with the group of Suarez and many other people in the community of complex network, we have been developing algorithms to break the giant connected component, right? The typical percolation problem. And then we decided that this was a perfect time to apply all these ideas, all these algorithms in a realistic setting and to understand the spread of COVID-19 and see whether we could actually use all these algorithms to break the giant connected component in this particular case. So we put together all these students and postdocs between the two labs, and we started to work in March 2020. Now, we wanted to do a very realistic approach. Essentially, all these algorithms has been tested with all sorts of different networks, Erdo-Renshi, scale-free, in certain also realistic settings. But here we wanted to do it on the particular case of the transmission chain of COVID-19. And we realized that we needed big data, right? We needed realistic data. And then we contacted our friend Matías Travisano, who is the CEO of a company in California, in San Francisco, called Grand Data. And he provided an amazing data set of geolocalization of a million of people with billions of data points across all Latin America. This database is based on GPS geolocalization from mobile apps. And with that data set, we actually were able to define the connected components and study the problem in a very realistic setting. But we, of course, realized that we needed real data on patients, of COVID-19. So then we contacted Antonio Lima Neto from the Epidemiological Surveillance Unit in the government of Fortaleza. And he provided data on COVID-19 infected people, patients. So we were able to match these two data sets, the data set of patients with the data set of GPS geolocalization, and perform a very precise contact tracing protocol in the city of Fortaleza and beyond. And this is what I'm going to show today. Now, I would like to start discussing why contact tracing is important in this particular case. In principle, here we have two striking cases, right? So we know that in USA, we are still having cases at the level of 100,000 cases per day. We go already to 45 million cases and counting. That's actually the same case in the big three, let's say USA, Brazil, and India. The pandemic is still going. While at the same time, countries like China or Singapore or South Korea, actually, they were very successful in flattening the curve very, very early in the pandemic. So as of today in China, there are just 26 cases per day. So what is this difference? So why we have this striking difference? So we do not know, but what we know is that in China and South Korea and Singapore, there was a very strict contact tracing protocol applied very, very early in the pandemic. In the case of China, there is very little information. This is actually from the MIT Technology Review. But at that time, I was talking with my students and colleagues in China, and they told me that suddenly contact tracing app appears in Alipay. Alipay is an app that absolutely everybody uses in China. And there were very strict rules to circulate with 3 different colors, green, yellow, and red, and so on. So then perhaps that's the difference, and that's already tell us that the contact tracing is extremely important. I want to discuss a second feature of coronavirus that tells us also that in this particular case, in the case of SARS-CoV-2, contact tracing is extremely important. And we could compare the 2 cousin viruses, SARS-CoV-1 and SARS-CoV-2. In one case, in the SARS 2003, eventually we had only 8,000 infections worldwide. And now in SARS-CoV-2, in COVID-19, we are going over 220 million infections and with 4.5 million deaths as of today in the entire world. Why 2 viruses that are cousins in the same family of coronavirus, they have such a different spreading behavior? Again, we do not know, but the one possibility can be seen for this difference can be seen in the epidemiological profile. So what we see here is that in the case of SARS-CoV-1, right, you are exposed to the virus, you have certain symptoms, right, and then the period of infection, the period of infectiousness when you are infecting other people, pretty much coincides with the peak of the disease. What is important is that it happens after the onset of symptoms. So this is actually in average. It's not that in all the cases it's going to be like that, but in average, infectiousness comes after the onset of symptoms. What it means is that when you start to feel sick, if you stay at home and if you go to the hospital, if you isolate yourself, then pretty much you stop the disease right there. You do not transmit the disease to other people. The case of SARS-CoV-2 is exactly the opposite. You are pre-symptomatic when at the peak of infectiousness, like what we see here in this profile. So essentially, you start with the symptoms, you go to the doctor, you get a test. 2 days later, you know that you have the virus, but you already infected everybody 2 days before you started with any symptoms. And the situation is even worse because there are asymptomatic cases, of course. So then this tells us that the way to stop the disease in the absence of a vaccine is by going back in time, in the case of SARS-CoV-2, right? To do a strict contact tracing to catch all the contacts that you have been generating at the peak of the infection. So we decided to attack this problem with the network theory. So as I said before, we have been developing, not only us, many people in the community have been developing all these algorithms to break the giant connected component through optimal percolation. Also, we know that the virus spread in the K-cores. And we're going to combine all these ideas to try to apply these, these algorithms to a very realistic case of the real spreading of COVID-19. We're going to end up noticing that an idea of granometer, the idea of a strength of weak ties, will allow us to identify the people that we need actually to isolate in a directed quarantine to break the giant connected component. And we are going to add a lot of data to the mix. Now, typically, we want to bring epidemiology to the age of big data, right? So typically in epidemiology, we are using models that have been developed over 100 years ago. They are called compartmental models. We put people in certain compartments, in certain boxes. Typically, we have the susceptible, exposed, infections, recover model, SEIR, but there are an infinite number of combinations. You could put as many boxes as you want. And these are actually mean field models, and policymakers are been basing their decisions on these models. We wanted to do something more microscopic. There are certain simulations with the agent-based models, but here we want to take these models and then put them in a real network. So then we combine our efforts with grand data, and then we got this big data set on geolocalization, also including the patients. We're going to define very precisely the contact network of transmission, and then we are going to apply a big machinery of network theory to break this network, this contact network, with minimized interventions, right? So we want to extract the minimal number of people that will stop the disease, spreading disease successfully. So this is pretty much the pipeline that we apply. So we start with big approvals because we are, of course, dealing with very sensitive data, right? This is geolocalization of millions of people, GPS data. This is obtained from hundreds of apps that are being collected together. And we know where these people go from home to work. So it's a very, very sensitive data set. Pretty much every time that you use an app, you are consenting, right? When you click a button, which is the terms of services, you are consenting to your data to be shared with third parties, and this is what's happening here. So we also have the consent of the authorities of Fortaleza to use the patient data. We combine them, and then we have this very accurate spatio-temporal transmission chain of coronavirus, and we will apply the machinery of networks and some artificial intelligence to break this network with the minimal disruptions. So here, so here we see an example of two trajectories, two people in our data set. I hope that you could see the map of Fortaleza in the background. The two dots, the two orange dots, are two hospitals in the city of Fortaleza. And we see the trajectory. So these are people that are actually going every day in the morning to work in the two hospitals. So this is a case of a contact, right? That will possible transmit the disease. So this is how accurate is our data. So we have this anonymized, consented GPS geolocalization of millions of people from 100 mobile apps across all Latin America. So we could expand this across Latin America, and we are doing it actually across the world. So this data cover the entire planet. It has been used by the United Nations in a partnership with Grand Data. It is, of course, encrypted. There are billions of data points across all Latin America. It covers pretty much 5 to 10% of the population. Okay, it's a good coverage, but definitely it's a sample. And we test that there is no sampling bias regarding geography or regarding even age, gender, or economic status, because it could be that this is an Uber app and only a few people, young people, use that app, and then it may have a very, very bias built in the data set. So we tested that it's pretty much quite uniform. Now, if you're interested in problems of privacy, how this data is actually around, again, all this is consented through these terms of services. It's pretty much the same data that everybody is giving to Google every time that you use a Google map or any app that has even sometimes you're using a calculator and you are sending GPS geolocalizations to the owner of the app, and that's actually usually consented. You could actually go to sites like the timeline of Google or Google Takeout, and you will see all the trajectories that Google have been obtaining about yourself over 10 or 15 years of time. Okay, so the contact model, we're going to calibrate this model with real data, but pretty much it has built in a probability of contact, which has a spatial component and a time component. So there are two parameters. We build a circle, okay, of a radius r, and then a time t, which is a time where two people are within this circle. And then we calibrate this model with real data, with the basic reproduction ratio number, which is in the case of Fortaleza, it was 2.76. And the numbers that we got is that you have a high probability to be infected when the contact radius is 8 meters and you stay there for more than 30 minutes. So we were able to reconstruct the real transmission tree from patient 0 arriving at Fortaleza on March 8, which is the black dot that we see up there. And then, of course, this is not the full contact tree. You see that it's not even connected, but it is consistent with the 4 or 5% coverage of GPS data that we have in the city of Fortaleza. So starting from that, then we build up our contact tracing model. So we have seen already this epidemiological profile, this infectiousness profile. All these numbers are approximate, and we want to be more conservative than the numbers that we see here. But we have the latency, we have the incubation, we have the infectiousness period, right? The disease. Putting all this together, the data that we get from the doctor, from the patient, from the hospital, is the onset of symptoms. So we know that this person has been infected, and we know when the symptoms started. It's actually reported to the hospital. And then from that time, we go 14 days back in time. We look at all the connections, all the contacts in the contact network of GPS data in order to cover the infectiousness period, but also any contact, any exposure that came from another person, which could be even asymptomatic, right? So going back 14 days in time, we perform contact tracing, we build the network of transmission, and then we go a little bit after the onset of symptoms, 7 days after. So we have a period of 21 days over which we look at all the contacts of this infected person, and then we go layer by layer. We started with the black dots here, the COVID-19 patients. We go to the first layer, the red dots, the green, the cyan, and so on, and we build the contact network of spreading of the disease. We stop at the fifth layer because we are looking here for the giant connected component, and that's what we need. But you could stop at any layer that you want. In principle, typical contact tracing will stop only at the first layer. Here we keep going because we have the capability to obtain, the full network of connections. So at the same time, we know that in Fortaleza on 19th of March, it was applied, and across across Latin America, it was applied a very strict quarantine, mass quarantine, right? So then we want to understand the evolution of the giant connected component across this quarantine, and we see what's happened with this GCC. But anyway, so what we see here is that since we have localization, right, we have the data localization, we see that the quarantine was very effective. We see here that the mean square displacement of people was of the order of 1 kilometer per day, and then it dropped to 400 meters, a drop of to 40%. So it was quite strict, and there are countries in Latin America like Argentina that was even stricter. So it was it was reduced 80%. So it was very, very strict, massive lockdown. Yet the reproductive ratio didn't go below 1. It's still above 1, and that's the reason the pandemic kept spreading. So why is that? So let us take a look at the giant connected component. So this is actually the black curve that we see here. We normalized it to 1 before the pandemic, and we see that before the quarantine, and we see that after the quarantine, it dropped to 10% of its value. So again, the quarantine, the mass quarantine was very effective in destroying almost the giant connected component, but it didn't destroy all of it. So we'll see that this 10% is enough for the spread, for the virus to keep spreading. And in fact, we see that the reproductive ratio changes from 2.76 to 1.2. So it didn't go below 1. So just there, it didn't drop below 1. Otherwise, the pandemic could have been stopped just with the massive lockdown. But anyway, when we look at the trajectory of the giant connected component, before the quarantine, we see this hairball, of course, because everybody's having hundreds of contacts per day. So we actually open a window of 15 days, and then we run our algorithms, we build the giant connected component, and this is what you see here in the upper left part, this hairball, highly connected, and of course the disease there could be transmitted quite easily. After the quarantine, what we see is this structure of clusters. So it was very effective in reducing this hairball to this clustered structure with very tenuous lines connecting different clusters. So we will see that the structure here is the structure of the K-core. But we see here that still there was a giant connected component. So unfortunately, the quarantine was not enough to break completely this component. So we need to do extra things. So we need to, and here is where we come with the contact tracing, and then we will try to, the contact tracing protocol to try to destroy this connected component.
Matt, sorry, we have 5 minutes, okay?
5 minutes. Okay. I have 6:20 here. Okay, I'm gonna go a little bit fast. Okay, so I assume that everybody knows about the K-core. When we look at okay, because I have until 25. Okay, good. Sorry about it. Yeah, okay, so then when we look at the K-core, there is a very nice K-core structure, right? And we differentiate the inner core, the half a core of the network, with the half a shell of the network. So, and then we monitor these two components of the network. And what we see is that the half a shell, the periphery of the network, was pretty much destroyed by the quarantine, but not the maximal cores. So the virus kept spreading in these maximal cores. And then we apply here a series of algorithms to try to break these cores. Now, there is an enormous industry on algorithms trying to break the giant connected component. Here, I'm going to show only 3. Some of them were developed in my lab. Unfortunately, these 3 did not work in this particular case. If we look at the K-core, we could actually attack the K-core. This is not optimal because, of course, the K-core is made of people that are highly connected there, and there are a lot of people there. So that's what you do not want to touch this K-core. On top of that, the K-core of the network is composed of contacts that have been produced by essential workers. We will see that these are the people that go to the hospitals, to the warehouses, and you cannot quarantine these people. So the K-core is not a good approach here. You could actually attack the hubs. It's also not good because the hubs are very deep in the K-cores. We have actually an algorithm called collective influence that uses optimal percolation, also does not work, because they were defined, these algorithms were designed for sparse networks, for Erdos range and so on. And the network here is not sparse. It has a very particular structure with a sparse part, but then also with these big K-cores. So the one that is the best strategy is the between centrality, right? And if you have any experience with these algorithms, you will see immediately that you have big clusters, K-cores, then connected by this low degree between centrality. So pretty much by identifying these people with high between centrality, we could destroy the giant connected component with 1.6% of removals of isolations in the network. And this is actually the best strategy. It's better than collective influence, better than K-core, better than degree, of course, randomness, and any other strategy that we actually tested. And this is consistent with the idea of granometer. So here, this idea of weak ties is actually what gives you the best strategy to break the giant connected component. Okay, so where are these K-cores, right? This is that they're actually, they keep the pandemic alive. So we actually can geolocalize. Okay, one thing is to look at the network, but then we can geolocalize every single GPS contact, right, in the map of Fortaleza. And then we see that these are actually real people working in hospitals, right? The 3 main hospitals in the city of Fortaleza corresponds to the maximal core in the system. So these are actually people going to the hospital, essential workers that you cannot isolate, you cannot quarantine. They have to keep working. So the strategy then is to keep these people working, but break these big clusters, these big K-cores, by applying a very surgical quarantine to the people that are in between, which are, for instance, the 2 people that we see here in this video. All right, so then, so then in let's say some sort of a conclusion, we see that we can't really deploy an intelligent quarantine. Okay, it will start in principle with the mass lockdown, right? Because you need to actually reduce this huge hairball GCC to something treatable with network theory, let's say. And indeed, it was reduced to 10% in this real setting of Fortaleza. But then this is not enough. Unfortunately, this is the reason why, even though there were lockdowns everywhere in the world, the pandemic kept going. It's not enough because we have these K-cores, these essential workers, or may not be even essential workers, right? In this particular case, we see these K-cores that are still spreading the virus. And there is where contact tracing and a very particular protocol for isolation can break these K-cores and can provide the best possible quarantine with the minimum number of disruptions, right? Because you want to let the essential workers to keep working. So as just to finish, let me tell you that we actually try to implement all this machinery in a real contact tracing app, working with the government of Fortaleza and the Universidade Federal de Ceará. And we did build these algorithms in the back end of a contact tracing app. Unfortunately, we were not very successful. The app was not able to recruit people to download this app, and this happens across the world, and essentially due to issues of privacy, right? So people are not very happy by sharing this type of information, geolocalization with the government. But anyway, beyond these privacy concerns, what we have learned is that, okay, there is a way to destroy this 10% of the GCC, of the giant connected component. We could perform these smart, optimized micro quarantines with big data, right? So using the technologies that are available, because as I said before, everybody's sharing this data all the time, right? So even if you have issues of privacy that you do not want to share in this case, because here we are telling you, okay, we are going to use your data. But the companies like Google, Facebook, and everybody around in IT, they are actually using this data permanently. You are sharing freely this data with them. So unfortunately, due to these issues, it was not very successful implementation, not only for us, but across the world. In New York, also, we have a COVID alert NYC that is not really being used by anyone. But anyway, we believe that there is a certain opportunity not to do this contact tracing at the large level, at the level of a city, of a state, but perhaps in a small setting like a campus in a university, where the university, the authorities can decide, okay, we want to implement this for the people that enter into the campus and try to contain the spreading of the disease at this local level. All right, well, thank you so much for your attention. And yeah, I will be happy to answer any questions.
Yes, okay, Hernán, very nice talk. Thank you for your talk. We have time to some questions. You can see directly in the chat. We have 2 questions. If you can read and answer, please.
Yeah, Gabriela, she wants to know about the data collected from Uber app. How was contact defined? Okay, so the contact model is this one here, right? So we have the geolocalization of the people. It's actually quite tricky because you don't have every second or every microsecond or every hour. Okay, this changes a lot. So we have a ping from the app, and then we know this person is here, here, and here. Now, sometimes we know that this person has been for 30 minutes on a given place, right? And then the app is actually pinging a lot of data points. We reconstruct this trajectory. We reconstruct the trajectory of every single person in the data set. And if these 2 people were in a region of 8 meters, it's not 6 actually, that's actually for our model, right? To fit our data. 8 meters for 30 minutes together, then we put a contact. Okay, and then with this contact, we develop the contact algorithm, and we define the GCC and so on. All right, we have one question from Sebastian. It seems that the FICO identifier may coincide with the main modules of the remaining GCC. So yeah, so here the FICO, let's see the structure of the course. Yeah, so this is the structure. I'm not sure. Yeah, definitely, let's say there are other ways to identify the modules. If you do a modularity approach here, yeah, I think you will find pretty much the same modular structure, right? Because a module is pretty much a 5-core, a 6-core. Here, the largest core is 7. Okay, so then, yeah, most probably the K-cores also, yeah, they coincide with the highly modular structure of the network, definitely. Yeah, that's a good point. All right, I think that's all in the chat. If there is any other question.
Yes, there are no questions at now, but if anyone have to intend to perform other questions, Hernán can answer directly in the chat, okay?
Okay, perfect.
Thank you so much for your nice presentation. Can stop sharing, please. Okay. Our next speaker is Professor Andrea Rapisarda from Catania, Italy.
Thanks. Nice to see all of you, although in a screen. May I start?
Yes, thank you for accepting the invitation.
Yeah, so let me share the screen then.
Okay.
Okay. I have a problem with the accessibility. Sorry, 1 second.
Okay.
Okay. Sorry, I have to leave and start again. Okay. Let me see if I can share now. Okay, it seems I can.
Yes.
Do you see my screen?
Yes.
Okay. So let's. Okay.
Okay, it's in full screen now.
Okay, so again, many thanks for this invitation. I'll try to talk in these few minutes our project, our research that started actually some years ago, which is investigating the role of talent and luck in getting success. It may seem something strange, but I'll try to convince you that there is something quite important, not only in science, but also in our society. Okay, so seems let me doesn't move. I don't know why. Okay. So this is the team, the original team. Part myself is Alessandro Pluchino, who is a physicist working in the same department, and another colleague here in Catania, who is an economist, Alessio Biondo. So the motivation of this talk is chance important in scientific discoveries? How important is luck or randomness in our life? And is true that the most successful people are also the most talented ones? And if this is not, how we could do to improve the efficiency of our society? So these were the questions that we asked when we started this project. And you know very well that we have in science serendipity, which is discovery by chance. And actually, if you think a little about it, almost all discoveries are made by chance. In what sense? Just a few examples. Alexander Fleming discovered penicillin because he forgot a window open, leaving his laboratory, and some petri dishes were contaminated by some spores, and he won the Nobel Prize just for that. Of course, he was smart enough to recognize that this was important. This is not to be forgotten. But there are many others. For example, he was doubly lucky because another guy 35 years before him, an Italian, Vincenzo Tiberio, just discovered penicillin before Fleming, but he was living in Naples. He was just a student when he discovered it. Then he got a degree and he published this result, but nobody paid attention to this result. So it was soon forgotten. And other example is Arno Penzias and Robert Wilson, who discovered the cosmic microwave background just by chance, just working on an antenna at the Bell Labs. And or the most recent discovery by Gaiman Novoselov, who just playing with a pencil and some scotch discovered graphene. And we know, all of us, how important is graphene today for its fantastic properties. So there are actually many examples. Okay, the www protocol, for sure, Tim Berners-Lee could not imagine the impact that his invention in this case could have and we know very well today. But there are other recent papers that illustrate this thing. For example, this nice paper by Fortunato and collaborators, who just discovered that you can publish your most important paper at the beginning of your career, like Frank Witzek, in the middle of your career, or at the end when you retire. You have the same probability to write a very good paper. And so luck or randomness, chance, as you want to call it, is very important. But are the most successful people also the most talented ones? For sure, success can arrive just by chance. And for example, the most famous painting by Leonardo is La Gioconda, but for sure is not the best. It is so famous because it was robbed, and then it became very, very famous. Or think about J.K. Rowling. He had to submit her manuscript 12 times before a young child was so much interested that finally she convinced the editor to publish his book. Or consider name. Name can favor you a lot. There are studies about that. Or for example, in academy, of course, if you have a surname with the initial at the beginning of your alphabet, for sure you are more known than your collaborators. Or on the other hand, you can have a car accident, a disease, and this could change completely your career. But also for diseases, I mean, it has been discovered, for example, that even if you live a very healthy life, you can have cancer just because of replication of DNA, which could have random mistakes. So the more you live, the bigger is this probability that there is a mistake in the replication and you get cancer. And this probability is not so small. So that's why we started this project. This is the paper that was published just in 2018, sorry, with Alessandro Bruchino and Emanuele Biondo. And now I'll show you the result of this paper. We started from two well-known facts. First of all, that IQ of people is as usually a Gaussian shape. For us, this is just the proxy of talent in some sense. And this means that most of the people have more or less the same talent, and very few have talent, or in this case, an IQ, which is 2 sigma or 3 sigma bigger. And on the other hand, if we want to use as a proxy of success the wealth, we know very well that Pareto discovered this 80-20 law, in which actually you have a lot of people which are not so rich and very few who are very, very rich. So we have a power law in this distribution, which you find almost everywhere. So we have to reconcile these two things. How is it possible that people who have the same more or less talent or IQ then have completely different careers or completely different success? And so we devised a very simple model, which we call talent versus luck. It's an agent-based model. We have a working period of 40 years, 1,000 agents who have a normal Gaussian distribution of talent. And in their life, they encounter lucky events in green and unlucky events in red. And every 6 months of this 40 years life, we check if they have encountered a lucky event or an unlucky one. And they all start with the same initial capital. So now the dynamics of this model, you can increase, you can double your capital in a way that is proportional to your talent if you encounter a lucky event, or if you encounter an unlucky event, a red one, you just halve your current capital. Okay, so very, very simple model, but in order to see if with this simple dynamics, we could in some way reproduce what we observe around us. And okay, this is our world, I mean, with 1,000 individuals, and with this fluctuating lucky and unlucky events. This is our initial normal distribution for talent. And these are the first results. The first results, as you can say, is that those people who at the end of these 40 years have the highest capital are not always, or very seldom, are those who are the most talented one. In fact, as you can see here in this plot, usually those who have the highest capital, the biggest success, are just in the middle of this talent distribution. This is another plot that shows the same thing. That means that those who have gained a very big success, a very big capital, are just those who have encountered a lot of lucky events. And on the other hand, those who are very poor are those who have, independently of their talent, have encountered a lot of unlucky events. If we repeat this simulation many times, then we discovered that it is possible to reproduce the Pareto law, a power law with a slope minus 1.3. And again, these are the winners of each run. You see that you have those who have gained more are mostly around the middle of the talent distribution. So the most successful individuals are only moderately gifted, not the most talented ones. Here is just another plot with more runs, but it's just the same result. So we have a big problem. What is this problem? This problem is that usually we give rewards and honors to those who have had the most biggest success, but these people are usually not the most talented ones, but more often are those who are the luckiest one. So we have a naive meritocracy in this sense. And this, okay, we have shown it with this model, but we can observe it every day actually. So how it is possible to then solve this problem? I mean, and a possibility is that to redistribute some funds periodically in order to give another possibility to the most talented agent, in order to be able that these agents can emerge and be successful. This is not because, not for a question of justice, but it's also because the most talented people who have success could be more useful to society in general. So, so we imagined an efficiency of our system, which is the ratio of the people with a talent bigger than 1 sigma. So in this case, bigger than 0.7 with respect to the case of no funding case, with this is normalized by the total given funding. The result of this is reproduced here. So you see that we can actually redistribute every 5 years, in this case, some money, some units of capital to the agents in order to let the most talented one to emerge and be successful. And we can actually measure how better we can do with different strategies of redistribution. And actually what we use usually, which is giving rewards to the best, is not the best strategy, because you see that these kind of strategies are in the tail of this plot, and these are the worst strategies, because we tend to give rewards always to the same people. On the other hand, if we redistribute in a random way with certain percentage, or if you give even a small quantity of capital, but to everyone, this is the best strategy to give another chance to everyone and to have the possibility to let the most talented people to emerge. This is done with different funding capital, because okay, you can redistribute with different total funding, but I mean, the results are the same, that the egalitarian random strategies are always the most efficient ones, or you can do the same thing with the same amount of fixed total quantity. In any case, the egalitarian strategy and the random one are always the best strategies. Of course, you can use also something in between. You can give rewards to the best and half of the total funds and half of the total funds to the others in a random or equal way. So that, okay, this is the result of our model, but actually this is a problem that has been already studied. For example, in this paper, Big Science versus Little Science, the authors studied how the distribution of funds for research were distributed to different strategies, and they found very nicely that giving funds always to the same people because of their past was not so efficient, because this was did not stimulate those groups to produce more than before, than in the past. On the other hand, you have a big problem, because you encourage conformity instead of diversity. And diversity, we know, is very important in nature and also in research, because if you always study the same thing, there is no way in which you can find new things. So, and this is quite important. This is an editorial by Nature of some time ago. And so people is actually really trying to share and to give funds in different ways, also in random way, because you eliminate also the time spent in writing proposal. So you can at least have to reach a certain quality, and then you can give them a random amount, or maybe not so much, but just the possibility to start their research, even for crazy ideas. So the first conclusion is that we have presented a simple toy model which is able to reproduce a lot of stylized fact, and also a way in which you can overcome this naive meritocracy that is really around us, even if very often we don't realize. But okay, this study was quite lucky because it got a lot of attention. And then we want also to see how robust was this, and if we could also understand it in more detail. In fact, we started a collaboration with Damien Challet, and we studied a simpler model which could be solved analytically. And in this simple model, we consider only lucky events. Also considering lucky events, so you can have a power law. We consider a longer simulation time and more agents. And actually, we found essentially the same results. It was, on the other hand, not possible to solve the problem analytically unless you make some assumption that the talent is equal for all the agents, or is heterogeneous but distributed in a uniform way. So in the most complete model, I mean, there is no simple analytical solution, unfortunately. And finally, we started a collaboration also with Paweł Sokowiec from Poland and Robert Frank, who is an economist from Cornell. And we studied some data on sport competition, and also tried to reproduce this data with an agent-based model. And what we did actually was study the data from 100-meter sprint Olympic Games competition from 1968 to 2016. And then we compared this result with an agent-based model in order to see also in these repeated runs how luck and talent could be important. And actually, in this case, we consider tournament with different rounds. We started with 1 million agents, and then they were divided in 10 groups. At each round, you took only the first, who was the winner. And so in 6th round, you have the winner of all the tournament. We repeat this many times, and we can calculate the performance, which consists of a part which is given by talent and another part which is given by chance. And then we have a parameter which measures how important is talent. And with this, actually, we found that when you increase the importance of talent, of course, this distribution shifts to the right. So talent is more important, and there is no overlap among this distribution among the different rounds. And what you see on the data, on the other hand, is that you have some fluctuations, and the performance, of course, increase when you get to the final. You can calculate, in this case, the performance by considering the world record time with respect to the time of the single sprinter. And of course, the closest to one, the best is the performance. And then we compare the performance of different runs of these sprinters taken from data with those taken from the model. And we could estimate, of course, within our model, that luck or chance is important also in these repeated competitions. And of course, it's much less important than before. It can be considered kind of lower limit estimate. But there is also a difference between men and women. For men is 4%, and for women is 6%. And this is the web page of the project. And thanks for your attention. I hope to be inside my time, and good luck. So thank you again.
Thank you, Andrea, for a nice talk. We have some questions in the chat.
Sure. I cannot see unless I stop sharing. So let me stop sharing so I can see.
Okay. We have first a question from Max San Miguel.
Yes. Can you read it?
Max, if you can ask directly to Andrea.
Yes. Hello, Andrea. Very nice talk. You address a very interesting question, and you have nice results there. Now, of course, the question of success is, I mean, what's the indicator of success? I mean, it is clear when there is a competition. I don't know if every scientist would agree that a way of measuring success of a scientist is in the amount of funding that the scientist gets. But anyway, my question is more on the role of incentives. I mean, there are many talented people that they do not have an incentive to become successful, for instance, economically. And I don't know if that's something that could be introduced in your model. I mean, coming back to scientists, I think that most very talented scientists being successful is not their largest incentive.
Yes, no, let me answer your question. I mean, actually, we were motivated by this because we see around us a lot of very talented people, very often young people who have no possibility to have a career. I mean, success in this sense is just having a permanent position or just having the possibility to publish, to have funds for their research. And very often we, on the other hand, see that funds, especially in research, are redistributed always to the same groups and to the same people, to the same university, and so there is a bias in this sense, and so it would be much nicer and I think more efficient in general for research itself to give a possibility, maybe not that much, also to young people, to people who have not passed and have not demonstrated maybe their capability because they were not able to publish in Nature or in Science. And very often we know that in order to publish in these journals, you need to publish it with very well-known scientists, otherwise it's almost impossible. So I think we should have the courage to give a possibility also to strange ideas. When we evaluate a research project, very often we are biased by our prejudice. And on the other hand, if you think of flying machines at the beginning of last centuries, they were considered crazy people, but only after a few decades we could fly everywhere, and we are on the moon, we go to Mars, and just because of these people, just because we gave a chance to these pioneers, and or at least someone gave them a chance. That's the point.
I agree with what you say, but I still would be nice to be able to introduce in a model like that the incentive for success, because here it is the same for everyone.
Yes, no, sure, but I mean, this is something that goes to our societies, but also in our private life. I mean, we should give every day a chance also to very strange ideas of some collaborators. I mean, because very often they are not biased by our prejudice, and they could be right.
Thank you.
Okay, thank you. I have another question from Felipe Alves. If you can ask directly to Andrea, please.
Yes, please.
Hello, can you hear me? Okay. I wanted to ask about the connection between the distribution of lucky events and the possibility that there's a connection between talent and the ability to find more higher density regions of lucky events. Because, for instance, if you are a scientist or a young scientist, you're trying to find a place to publish. If you go towards a newer areas of research, you're more likely to find some possibility of publication if you go to classical mechanics, for instance, something in slides.
Oh, yes, this in some sense is something that we considered in the talent distribution. Talent is not, in our view, in our simple model, is not only the your property of being or having a very IQ or very resilient. I mean, but also if you recognize that there are more possibility to work in one direction with respect to another one, you go in that direction. For example, I mean, like if you live, I don't know, in Nepal and you want to be a physicist, it's better that you move to some other place, probably. But if you want to be happy and live without studying physics, probably it's better that you stay there. So, I mean, it depends. Of course, this is part of your talent. I mean, trying to find the opportunities, because, I mean, this doesn't mean that you have to wait for something that comes from outside, but you also have to look for your opportunities. And if you stay in your office waiting that something arrives, this is very improbable. That's for sure. So that's part of the talent in our view.
Yeah, but in the model, the distribution of opportunity of lucky events is completely independent of the talent, right?
Yes, sure.
And the talent and the movement of the agents don't consider the region.
The agents are fixed, but of course we need a lot of repetition. The only things that moves are but not that much. In a random way, are the lucky or unlucky events. Okay.
Okay.
But this changes every time. So I mean, it's in the end, if you make an average over 100, 1,000, 10,000 repetition, then all this is averaged.
Okay, thank you.
Okay, thank you, Andrea. We have other questions in the chat, but we have other speakers. We don't have time
to answer.
Thank you. Yes, you said yes. Okay, thank you again. The next speaker is Marco Antonio Amaral from Brazil. Marco?
Yes, can you hear me?
Your sound is too low.
Too low? Okay.
Yeah.
Let me try to change here.
Yes, it's
Just
better.
1 minute. It's better? Is it better? Okay.
Yeah.
Perfect.
I can hear you fine.
Should I share my screen? May I?
Okay.
Is it okay? Perfect. Can I start?
Yes, you can start.
Thank you very much. Thank you, all organizers here, for this chance, this opportunity, and everyone here. So I'm going to talk just a little bit of some models that we've been working on, and they are focused mainly on different, let's say, imitation rules, update rules for game theory. And I just want to make a quick introduction, but we all know that game theory, classical game theory, is mainly focused on finding the best strategy in a decision-making process, let's say. And we have the classical prisoner's dilemma and other games that we have, let's say, 2 strategies or even more. And we use mathematics to choose which is the best strategy or the Nash equilibrium and so on. This is the classical game theory. But eventually, Maynard Smith will have this amazing insight to think of strategies as an evolutionary process. And then the question changes to which strategy is more evolutionary stable. This is deeply based on evolutionary processes, and this comes with the idea of reproduction and birth-death processes. So what I'm trying to say is that usually the reproduction of a strategy is based on what we call imitation rule. You try to imitate best strategies or better faring strategies. And this makes a lot of sense when we are dealing with evolutionary processes, when your son will inherit your genetic features that make you have one strategy or another. This gave us a lot of insights on how strategies can evolve in time in different species. Nevertheless, we can also look at strategy evolution from a cognitive point of view. I mean, we know that humans do not only imitate other strategies. We are creative, we can innovate, we can create our own strategies without having to imitate one another. And our work here focused mainly on this aspect. What are the differences between when I imitate one strategy and when I am free to use other kinds of process that we call innovatives? So the main dynamics that we used is the classical Monte Carlo procedure here. We have a population in a time, and then we make each agent of the population play a game between one another to calculate their payoff. With the payoff of each single individual, they are able to compare their gains, and based on this, they update their strategy. So we have another time step and so on. We evolve the population until we reach some stable state, like the classical Monte Carlo process. Okay, this is just a quick introduction. I don't want to get too much into details here, but we can answer any questions of the technical parts. Regarding our model specifically, we used the most classical prisoner's dilemma game, so we can better study the effects of specifically the update rule, because our main question to answer here is how the strategy update phase can alter the population dynamics. So we use the prisoner's dilemma rule, and then we set the weak prisoner's dilemma, that is to say that we parameterize the game in a way that we can change the temptation to the effect. And then we get the classical parameter diagram. Here you can see the two main parameters in this kind of parameterization is the temptation to the effect, T, and this so-called sucker's payoff, that is akin to the fear of being betrayed. And here, if T is greater than 1 and S is negative, we have the prisoner's dilemma game. We also can parameterize this to other 3 types of game: the harmony game, the snowdrift, and the stag hunt game. But here we mainly focused on the prisoner's dilemma game, that is the most famous dilemma kind. And now the main part of our research is regarding how agents update their strategies. Usually, as I said, we use the imitative update rule. That is also called sometimes the replicator, because it's based on the replicator equation and so on. And in this rule, an agent that is surrounded by other strategies will accumulate its payoff. And then let's say the site on the right may compare its own payoff with the central site. And he looks at the central site, sees that the defector has a way higher payoff, and then updates its strategy, copying the central site strategy. In evolutionary terms, this would be the same thing as if the offspring of the central site have a higher fitness, so it substitutes the player on the right. And this is the most usual update rule we see in most of the evolutionary dilemma simulations. Each single player can imitate the best faring player around him. Of course, we have other rules that take into consideration irrationality and the probability to imitate or not the player. But the main point here is that they always imitate. Now, we know that humans, as I said before, can change their strategy spontaneously. An innovative update rule would be something that allows a single player, let's say the central one, to spontaneously change its strategy based on cognitive processes. Let's say he is a cooperator surrounded by other cooperators, and then he understands that if he becomes a defector, he would have a huge profit, reaping a lot of profit from the cooperators around him. This is what we call an innovative update. So, mathematically speaking, we used what is called sometimes the logit model, sometimes the Ising model, to implement the innovative aspect. What is this? A player here, instead of comparing his own payoff with its neighbors, he compares his own payoff. Here in the Fermi distribution, his own payoff is UI, and he compares not with his neighbors, but with his own payoff if he changed strategy. Here, in this case, he changes to defector, and then he calculates what would be his payoff if he changed to defector, and he calculates only between himself, his current payoff, and his future payoff if he changed to another strategy. And this will give the probability of him to change to this other strategy. This is what we call an innovative model. And of course, this is based on the cognitive analysis of anyone in the future situation. Okay, so
Marco,
yes.
sorry, 5 minutes, okay?
Oh, okay, perfect, thanks. So we compare this with the imitation rule. Thank you. And then here we have the classical diagram, the fraction of cooperators whole against the temptation to defect T. And we see that as we increase the temptation to defect, cooperation goes to 0 in the classical weak prisoner's dilemma. And now we present two different innovative rules, the easing rule that I explained, and in green we can see the win, stay, lose, shift. It's another innovative rule that when you're winning, you stay with your strategy, and if you're losing based on some parameter that you call loss, then you change to another strategy without imitating. And we can see instantly, we can see that this completely changes the whole dynamics of the population. More specifically, we can see that both innovative rules will lead to a basal level of cooperation that is independent of the temptation level, and it greatly increases the survivability of the cooperation in the model. Okay, so here are just some other graphs that we also explore this in scale-free networks and normalized scale-free networks, both with the easing imitation rule and the win, stay, lose, shift rule. And we can see that every single time the presence of the innovative strategy greatly enhances the survivability of cooperation. Specifically, it tends to create a small pocket of cooperators, even if the conditions are very bad to the cooperation. Here we can see the whole parameter space, and then we show not only the prisoner's dilemma, but the snowdrift and the stag hunt types of game for the imitation rule, that is the classical model. And then we can compare with the logit and win, stay, lose, shift dynamics. And we see that this is not only a localized phenomenon. The whole parameter space of all the analyzed games changes, and for better when we are looking at cooperation. The use of innovative dynamics is very beneficial to cooperation. And in this sense, I'm not talking of only the innovative rule of easing model, the win, stay, lose, shift model, and we also explored some other innovative rules. And we saw that when you are able not only to copy the strategy, but to analyze the situation and spontaneously change your strategy, usually you will have but you will have some cooperation, more cooperation. And this can be changed continuously also, because not everyone is an innovator. So we use the percentage alpha of the lattice being composed of innovators. And we see that they can create this effect of basal level of cooperation for any temptation to defect. Even if we have only like 10% of innovators, they can help sustain cooperation. It's not like only the innovators will be cooperators. They can influence the imitators around them to become cooperators too, because the system does not fall into stagnation, into frozen state. So this is the main conclusion of our model, is that we studied, here we presented the logit and win, stay, lose, shift innovative models, but we also used some other innovative models, and they all are able to maintain a minimum level of cooperation, which is very interesting because rational beings do not only use imitation strategies, they can innovate and change their strategies. We believe that this approach could lead to very interesting aspects of game theory, evolutionary game theory, especially when we implement other different kinds of innovative strategies. Okay, thank you. I'm already running out of time. Sorry for rushing things. Thank you very much.
Thank you, Marco. We have no time to answer. We have a question. I ask you to answer directly in the chat, okay?
Perfect.
To Max and Miguel. Thank you.
Thanks.
Can stop the, okay. The next speaker is André Martins from Brazil.
Hi, can you hear me?
Yes.
Good. I'll try to share my screen now. Let me see. Here. Can you see my presentation?
Yes.
Good.
Okay, André, you have 15 minutes, okay?
Perfect. Thank you. Thank you for the organizers for this very, very interesting conference. I wish you were all here in São Paulo so I could meet everyone in person. Sadly, we'll have to wait for the next time, but anyway, it's been very interesting. And I'll talk here very shortly about a problem that I have been working for a long time, and that's the problem of extremism, how it starts, how it spreads, and how we can do that. More specifically, more recently, I've been worried about how to define extremism, and you will see in mathematical terms and in terms of opinion models, and I will see why very soon. First of all, we have traditional opinion models for, and then traditionally we have two types of models. We physicists like discrete models because they are spin-like better. They are great for describing choices. You can describe the actions as well, but you don't have a natural definition for the strength of the opinion of an agent. On the other hand, you have continuous models like the bounded confidence models, where you do, opinion strength is natural, but it's not, the models are not so good to talk about actions. And when we're talking about extremism, action, if the person acts or not in the real world is a very important aspect of that. On the other hand, it's easier to say that if you are in the end of the range of possible results, you are an extremist. But is it really what we mean by extremism? Why the end, only the end of the range correspond to that? Okay, so we have opposing concepts here of what we mean by being an extremist. In discrete models, we can introduce them. Usually we speak about inflexibles, people who will not change opinions. So someone with extreme opinion is someone who will not change its views. In the continuous models, when you talk about the end of the range, we are not really talking about an inability to change one's mind. It may be associated to that. Some people do associate both things. There are ways to make the threshold smaller if you go to the extremes, but the extremes in themselves do not correspond to a smaller ability to learn. Okay, so we have conflicting. Those concepts are not the same in each case. So what I started doing was was proposing a model where I could talk about options, about choices, and I could also talk about how strength our opinion was. That was my original CODA model, where I defined it. People were looking between two options, two values of spin, or choice R A versus choice B, and there is a probability that one of them is better. Of course, 1 minus P, that's probability that's the other. You observe only the choices of your neighbors, and you update your internal probability using a Bayesian-inspired rule. Okay, In the CODA model, there was a very simple change of variables. It became a simple additive model, but it could lead us to very strong, very strong opinions, and the space of choices would freeze. And except for people in the areas between choices, almost everyone became an extremist. Okay, this made me propose a framework to work with opinions models, where you have an issue, a distribution of opinions, how you communicate your opinion, how other agents' mental models work, and I could use that for any kind of situation. So I checked how it compare with bounded confidence models. I showed that discrete models rules can be recovered as a limit when you consider your agent consider its own influence on other agents. It was easy to introduce contrarians. We could see the emergence of inflexibles, the work I did with Galan. We could also introduce concepts of trust and how the network of trust evolves. And more than that, I went back to that model and I thought that the communication could also change. In that original model, I was only speaking about the choice. Maybe people could see the strength of my opinion, but also the mental model could change. I could either be looking for the best option, or I could be looking for a mixture of options. I want to put something of A and something of B as my optimum choice. It turns out that communication is important for how extreme the opinions will go, but my internal mental model is absolutely fundamental. If I'm looking for the one best answer, I get extreme very fast. Okay. Anyway, let's run because I don't have that much time. And then I extended that model where I had only two possible options, two spins, to any number of options. Here we have a figure where we have the formation of domains for, I think this is 10 different possible options. And we can see that it's darker in the middle of the regions, signaling that people have stronger opinions there. To do that, the easiest way I found to do that is to model things making pairwise comparisons between choice 1 and choice 2, and then choice 2 and choice 3, and each agent would have all these pairwise comparisons, and they would end with their favorite choice by analyzing all of them. Okay, so when I extended that to since I did have this model, I thought, okay, let's see what happens if I go to a mixture of continuous and opinions, continuous and discrete opinions, by having my many choices existing over one-dimensional issue. In the first model, I considered that there was a symmetry between all choices, but now my choices are no longer symmetrical. If I have 5 choices, for example, one will be extreme left, the other center, and this has an impact on, depending on what the agent observes. If you are observing an agent in the extreme left, the relation between extreme left and left will not be the same as the relation necessarily between center and right, because things are over this one-dimensional political or economical or whatever the opinions are about are. Okay. What we see is that if agents assume that when the center is better, extreme positions should be less probable, the tendency to central positions becomes more strong. But if agents actually expect extremism to happen, even when the central position would be the best one, we do move to the extreme of the political spectrum here. Okay, so in these are those two cases. The colors go from red to blue, meaning more extreme right or extreme left, from red to blue, and with green and yellow and orange being the central positions. So extreme left, left, central, right, and extreme right. And we see that in one case we have a tendency where for extreme green, that is very, very strong positions about the central position. They are very, very sure that the central position is the correct one. And another case when they are very, very sure that either the extreme left or the extreme right are the best positions. But what's interesting here is this case where people were extremists about the central choice. That means that I have 5 minutes. Okay. That means basically that when we talk about very strong opinions, being in the end of the spectrum of the possible values might correspond to an aspect of it, but it's also very important to consider how strong people think about it. And in this model, I can have both ideas can be implemented. We can talk about extremists in the sense of being, if you have 10 possible options, option 1 and 10 are the most extreme because they are in this opinion axis, they are the most distant ones. But we can also talk about strength of opinion in favor of positions 4, 5, and 6. And we can also have very, very strong opinions there. So we need to discuss better what we mean by extremist. And of course, to do that, we need maybe one extra aspect of the problem, and that is actions. Here, I was only talking about how people think and what they express. If this expression is only verbal, there is no action. We don't see that as a problem in our society, so much of a problem in our society. It could be when people are defending that you should not take vaccines, for example, and then the discourse in itself can be problematic. But we also have problems with extremism where it's only when people actually commit violent acts that we are really, really worried. So action might also is still needing. So this is something that we still need to work. I still proposing the question, and that's basically it. So thank you very much. It was a pleasure to be here, and that's it. Thank you for the organizers one more time.
Thank you, Andrea. We have time to one question.
Okay.
You can see directly in the chat, okay? From Philippe.
Okay, let me keep here. Chat. It wouldn't a model that's agnostic to which opinions are, but rather focus on the internal mental model more appropriate. I'm not sure I understand what you mean by agnostic. Do you like to explain it a little bit better, Philippe, please?
Sure. What I mean is that you're trying to you define beforehand what is a positive opinion and a negative opinion and a central opinion, and then you have this effect in the end that you have extremists for the central opinions. But yes, maybe you could have like many different other possible opinions that you didn't consider at first, and you could have extremists for every other possibility.
Yes,
maybe
yes,
maybe the expression of the opinion is the action that you're seeking. That's the part that bothers me a little bit, because expressing opinions is already an action, and if you have the possibility of having different things to begin with, maybe you could find what I'm saying is, if you go a level deeper and you model the internal mental states that you mentioned in the beginning, you would be free to have any possible opinion, and then the strengths of the internal state would indicate if it's an extremist opinion or not. That's what I'm saying. What I was asking is why you start by defining that there is 3 types of opinion, or you fix this part instead of going to the deeper level, a little deeper level in modeling the internal mental state.
Well, you can have different models for how people interact. I'm not sure what I fixed in this case was I chose I choose a discrete number of possible expressions. We can call it actions, of course. They can be seen as actions. I was making a distinction in the end because sometimes those actions are just the discourse. So, and then we are, if we also worried about violent actions, you should need another level of action in this. But yes, if we're talking about vaccines, for example, the discourse in itself is the action. And then we could have we could have a scenario where only two choices are or maybe three, because someone might be neutral. But the model in itself, it does consider the mental models of the agents, because there is a likelihood matrix that I did not present. I had very limited time to speak. When each agent consider if this is the best choice, what is the chance that I will observe each one of the other possibilities? This is there. Okay, and if you get into the mathematical details, this is defined there. So every possible best scenario against every possible choice is how those interactions are defined, and how you get to one or the other case that I presented as final cases. As I had very limited time to get there, I didn't show you the mental model of the agents, okay?
No, sure.
But it is there. From that, we can extend. In this case specifically, I was exploring a number of limited discrete options, also as a means to explore and to compare discrete and continuous models. It was a way to pick discrete models and take them in the direction of continuous models and see what I would gain from doing that comparison. Okay, right. So it was a theoretical exploration in the limit between those two models to help clarify concepts that are different in each one, so that we could compare them. So it was also, of course, for an application, a real-world application, and I presented none. It was very theoretical. We would need to consider what really is an action in that problem, what really is the mental model for that case, how many options there are, and how to introduce those things. But if you want, I can give you more detail, but I think Nuno is close to...
Yes. Our time is over. Okay. Thank you, Andrea.
We can talk about it later.
Okay. We now have a break. Thank you, Andrea. Well, you now have a break. We come back at 10:45, okay, for the presentation of Victoria Shemeshenko.